Okay, so today we're talking interpretations and applications of the derivative and the definite integral. So, the derivative of some amount is the rate at which that amount is changing, right?
Yes.
So, we're good at this, right? The problem is when we try to go backwards, like Shane and I were looking at some of these problems for the that I gave you on the homework that were the FRQs, and it's asking you to think backwards. Like, given acceleration, what do you know about velocity and things like that, and trying to make sense of that, and my brain was like not working, and so but you guys know you can Google all these free response questions and figure out the answers and then if you are having trouble with that, come ask me questions, and we can go over what they should have been, and how to think better about it, assuming that my brain can work like that at that moment, but we'll see how it goes. Anyways, so examples. If water is being drained from a pool and R of T represents the amount of water, measured in cubic feet, that is in a swimming pool at any given time, measured in hours, then R prime of T would represent the rate at which the amount of water is changing. And if that rate is positive, we're filling the pool. And if it's negative, we're draining the pool, and things like that, right? Another thing that we noticed on the test was one of the grading guidelines was make sure you put units on things. So if a problem has units, make sure you're always putting units with your answers. There were a couple people that forgot that, and then that was why points were missed on the test, was because you forgot to put units on things. So always make sure you're putting units on problems. Okay, so what would the units of R prime of T be? Per hour, cubic feet per hour. Okay, so now we're going to go backwards with this. The integral from A to B of that rate, okay, is going to equal the amount of the change. So in the context of the above example, what does the integral from A to B of R prime of dt equaling R of B minus R of A mean? What does this represent? Yeah, the amount of change, or the amount of change in the water level from time equals A to time equals B. Okay, so we're going to put this like R of B minus R of A equals the integral from A to B of R prime of T dt. Represents the amount of change that looks like charge in the water level from time A to time B. Okay. So the table given below represents the velocity of a particle given at values of t, where t is measured in minutes. So we want to approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum. Using the correct units of measure, explain what this value represents. So how would I need midpoints, right? And I've got 1, 2, 3, 4, 5, 6, 7 values. So if I do it with this, then that's a midpoint. This grouping, that's a midpoint. This.
We get to choose our own intervals and stuff?
Yeah. But you need intervals where you actually have midpoints. right? So that was the only grouping we could have chosen.
Okay.
So give it a shot, and then we'll talk about it. So what did we get? 63 feet. Okay. So what does this represent?
And total distance traveled by car.
Yeah. Because it's all positive, so it's total distance traveled. Okay. So the amount of change in position, or of position, and this is total distance traveled, since v of t is positive, okay, from t equals 0 to t equals 30 minutes. Okay. Okay, what is the value of the integral from 5 to 25 of a of t dt, and using correct units, explain what this value represents? So how would I figure that when I just have this?
Minus v of 5.
Yeah, the integral from 5 to 25 of a of t dt is going to equal v of 25 minus v of 5. So that is 1.6 minus 1.6, which is 0 units. Okay. So, what does this represent? Mm-hmm. Yep. Yep. Okay. Oh, sorry. I have people still writing. Okay. Temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable function, W, where W of t is measured in degrees Fahrenheit and t is measured in minutes. Using the data in the table, estimate the value of W prime of 12. Using correct units, interpret the meaning of this value in the context of the problem. How would we do that?
The rate from 9 to 15.
Yeah, the rate from 9 to 15 or 15 to 9, that would help us. So W prime of 12 would be approximately equal to W of 15 minus W of 9 over 15 minus 9. So 67.9 minus 61.8 over 6, which is 6.1 over 6, which is approximately 1.017 degrees Fahrenheit per minute, right? What does that represent? And what is the temperature doing at the rate of 1.017 degrees Fahrenheit per minute? So, since W prime of 12 is positive, the temperature is increasing from t equals 9 to t equals 15 minutes. Okay? Using the table, data in the table, evaluate the integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning of that integral. Yeah, yeah. So the integral from 0 to 20 of W prime t dt is just going to equal W of 20 minus W0, which is 71 minus 55, which is 16 degrees Fahrenheit, right? And then what does that represent? Yeah. The amount of change in temperature from 0 to 20 minutes. Okay, lastly, for 20 times between and inclusive of 20 to 25 minutes, the function w that models the water temperature has a first derivative given by the function w prime of t equals 0.4 square root of t cosine of 0.06 t. Based on this model, what is the temperature of the water at time 25? So I would set this up as the integral from 20 to 25 of this function equals w of 25, oops, why did that do that? W of 25 minus W of 20, right? Do we know W of 25? No, the table only goes to 20s, but we do know W of 20. And use your handy dandy calculators to get that value. Make sure you can do this. And yes, I call them handy dandy because of Blue's Clues. My kids were raised on Blue's Clues. Blue's Clues was before you guys' time, wasn't it?
I watched.
Okay, good.
Don't do that to us.
Okay. It was really hard for me to even realize you guys weren't alive like for 9/11 or like I'm getting old. 9/11 was rough. I was living in Little Rock at the time. Working for an aircraft company. They shut down all the runways and nobody could go anywhere. And my company was at an airport on the airport grounds. It was crazy. Of course, it was Little Rock, so we were kind of used to higher levels of security because the Clintons would fly in all the time. And so, I mean, many days I went in, there were snipers on top of the building and stuff like that, just because Air Force One was coming to town or one of the other air forces. I got to see Air Force One in person. That was nice. I have classmates from college who got to like escort the president on and off the plane. You know, like they were the ones who would greet Air Force One, and like, too cool. One time I set my son up to talk to a classmate of mine he wanted to be a forensic accountant. So I had a friend of mine who was really good at tracking like illegal payments and corruption around the world. So I set him up to talk to her, because I thought, oh, this would be a good contact for him. And he's like, Mom, you didn't tell me she was a professor at Georgetown. Look, I didn't know. She's just my friend. Okay, so what do we get? Yeah, so W of 25 equals 73.043 degrees Fahrenheit, and we should have gotten 2.043 for that integral.
Do they care about like sig figs and stuff?
No, they're not real big on sig figs.
Okay. I'm just gonna leave it.
Okay, so sig figs. Everybody makes a big deal about sig figs. Here's the raw meat of what actually happens in engineering. you get one more digit than you were given, right?
Mhm.
And that's it.
You give one more than you were given?
You give one more than you were given.
Oh, okay, okay,
Yeah, yeah. You can go one more digit than you were given.
okay.
And that's the most you're allowed to go. So, now, that has nothing to do with tolerances, which are a separate issue established by safety professionals.
Oh, okay.
So, safety tolerances are in a whole different ballgame. Pan of biscuits. Ooh. I'm feeling biscuits and gravy for our practice test. I'm feeling it. I really am. Now, keep in mind, I used to run a restaurant.
Okay, okay.
Okay? I flat know how to cook. Okay, so if I'm bringing you breakfast, you're gonna like it. Unless you're just weird. Okay.
Bring some pancakes.
Pancakes are good too. I've got a waffle maker.
A waffle maker?
Yeah. I'll bring a waffle maker. I can do waffles. Yeah. Waffles sound good. Maybe some. Yeah, we'll do it upright. Because I can bring my crock pot full of gravy. I can bring biscuits. I've got an electric skillet to make some scrambled eggs. And I'll have pre-cooked some other thing. You will not go hungry.
I'm excited.
Sound good?
Yeah, it does.
Okay.
Very good.
Because you need good breakfast to take a test. Now, that being said, I can't do that the day of the test, but but we can have fun. Okay. Pan of biscuits is removed from the oven, at which point in time, t equals 0 minutes, the temperature of the biscuits is 100 degrees Celsius. Wow. The rate at which the temperature of the biscuits is changing is modeled by the function b prime of t equals negative 13.84 e to the negative 0.173 t. We want to find the value of b prime of 3.
You just plug it in.
Plug and chug. Right. So b prime of 3 is going to equal negative 13.84 e to the negative 0.173 times 3, which is approximately equal to negative 8.236 degrees Celsius per minute, right? So, what's happening to these biscuits? They're decreasing in temperature. So since b prime of 3 is less than 0, the temperature of the biscuits is decreasing. At t equals 3 minutes after the biscuits were taken out of the oven. Okay. We want to sketch the graph of b prime of t on the axes below. Explain in the context of the problem why the graph makes sense.
Are we supposed to use a calculator? Or do we?
Mm-hmm.
Oh, okay.
Good.
Okay, I
I
was like,
are we supposed to just know how to graph that?
Yeah, anytime you see decimals in your function, that's a calculator. Yeah. And if any of you have specific food allergies, let me know. We can work around that. For April 6th. See, that's my problem for breakfast. I like too many things. Now I'm thinking of your pancakes idea and thinking, wow, we could do a pancake bar where you just like pick your own toppings. But then I think of the logistics of that and it makes me not want But there's that. I've done that before. Sometimes we would do that for Christmas. Like a Christmas breakfast with a pancake bar, and you could just I would have like chocolate chips and blueberries and raspberries and pecans and stuff like that. All those things that are really good in waffles and pancakes, and then we'd set up, you just tell me what you want, and I put it on top of the pancake, flip it over, we're good. Okay, so you should have gotten something. Yay, Notability. It kind of looks like this, right? Huh?
Your first line was what it's supposed to be like.
No, that was the asymptote. No, that was the asymptote, right? So, what does B prime of T represent?
Which the temperature of the biscuits are.
Is, yeah. So, what does this graph tell us about that?
As the biscuits get closer to room temperature, the speed at which they cool down decreases.
Yeah, so the fact that this is below the x-axis and it's always negative, okay, tells us that the temperature of the biscuits is always decreasing, right? But the slope of that, you know, it's higher at first than it is, right? So it cools down a lot quicker, right? And that slope is always decreasing, right? And so that's going to indicate that the temperature of the biscuits is always decreasing, but it's doing so at a rate that's decreasing, okay? Because it's really high. Sorry, wrong pen. Slopes are high here, and then they keep decreasing here, right? Okay, so the fact that the graph is negative says that the temperatures are always decreasing, but they're doing so at a rate that's decreasing, right? So the biscuits are cooling, but they cool down really fast at first, and then not so much after a while, okay? And you could put more information about the slope and, you know, how that is doing increasing rate if you wanted. Okay, time t equals 0. What is the temperature of the biscuit? Yeah, I think we're doing biscuits and gravy and waffles and scrambled eggs with bacon and fruit, some OJ and water. Sound good? Because I can pre-make biscuits, pre-make gravy, pre-make the batter for waffles, pre-make the batter for scrambled eggs, pre-make the bacon, and have everything ready to go. So I'm scrambling eggs and making waffles fresh. Okay, I got it all figured out. That's my plan. Because because I've got a big crock pot for biscuits, a little crock pot for gravy. Yeah, we're good. And I'll find a microwave to reheat the bacon. Okay, what did we get here?
34.188.
And this should have been negative 65.817 there for that integral. Okay. Okay. Next one. Cylindrical can of radius 10 millimeters is used to measure the rainfall in Stormville. During the first 5 days of a 60-day period, 3 millimeters of rainfall had been collected. The height of the water in the can is modeled by the function S, where S of t is measured in millimeters and t is measured in days for days between 5 and 60. The rate at which the height of the water is rising is given by the function S prime of t equals 2 sine 0.03 t plus 1.5. So, answer these two questions. See how well you do on your own. What day is graduation?
19.
The 19th? Okay. So then your last day, senior's last day is the 15th, right? Okay. Oh no, I always cry at graduation and I always go to graduation. So just get used to it. They're like, you know, graduation is, you know, one of the activities you could choose from. I'm kind of not used to that. My last school made it mandatory, and of course it should be mandatory for teachers to be there. This is what we're all working for, you know? I want to see you guys graduate. Yeah. Means I did my job. You guys are going on to awesome things. And everybody has a plan, right? Or you're at least on the road to solidifying the plan. Everybody good with this? So watch out for these little tricky things like, hey, the first 5 days we put 3 millimeters in there, so we needed to add 3 millimeters to the total water level and then use that to calculate our volume of the cylinder, pi r squared h, okay? So lots of these little details kind of come in unexpected ways, but yeah, just note that that kind of stuff gets a little weird sometimes.
I put the same thing in my calculator, but I did not get that number.
Yeah.
Did you probably multiplied out the pi.
Multiply out the.
Oh.
This is pi.
Yeah, did you get 52,327?
Yeah.
Yeah, that's times pi. So 16,656.
Oh, they want it without the, oh.
Yeah, well, it's fine. If we multiplied by pi, it would be 16,656.5 times pi. So,
Oh, okay, I see.
52,329.9,
Okay.
27.9 millimeters cubed.
Yeah, that's what I got, okay.
Okay.
So both of them are.
Yeah, yeah. So keep in mind that it's okay to not multiply out pi because you don't want to spend any more time on this than you have to. You do not have to get it in simplest form. You have to get it into an equivalent form. And the first equivalent form you get to, go with it. Okay? So, I don't know. Yeah. It's okay as long as you don't make a mistake. That's the thing. You don't want to make a mistake and then that costs you points because then it's not in an equivalent form. Okay? So watch how much you simplify things. Okay? Because you don't want to simplify so much that you make a mistake and then cost yourself points. Okay. The rate at which people enter an auditorium for a concert is modeled by the function r, given by r of t equals that for times between and inclusive of 0 to 2 hours. R of t is measured in people per hour. VIP tickets were sold to 100 people who were already in the auditorium when the doors began to open. The doors will close and the concert begins at t equals 2. If all the VIP ticket holders stayed for the start of the concert, how many people are in the auditorium when the concert begins? Yep, go for it. This should be super easy. Twins. 6, 1, 6, 7. Oh, dang. Okay. Hold on. I gotta make some prints. Okay, so you should have gotten 1,080 people.